A large area analysis over a heterogeneous sample is an average over the analysis area. And to try and get a better feel for what it means to average over an analysis area, we'll have a look here at a gold grid over a void. So the analysis area consists of partially gold and partially nothing at all. So once we've loaded an element library and made the appropriate adjustments for the relative sensitivity for this particular instrument, we can create a set of regions on this survey spectrum to give us an idea of what you might typically get from a heterogeneous sample such as this one. Now it contains oxygen, carbon and copper and gold. The gold is a plating on a copper grid. So these are all impurities or contaminants that are on this surface. So we get a composition based on the survey spectrum that gives us an idea of what's there in terms of the analysis area. But it hasn't given us any indication that there were parts of the surface that had no signal at all. And we can see this if we do a measurement based on a sequence of images, where these images have been measured at different kinetic energies, and therefore we can construct a survey spectrum if we wished from these data. But more importantly, we have images that span the kinetic energy range, or at least some of the kinetic energy that were used in that survey spectrum. So what we're going to do is examine how the image of the sample, as transferred through the lens system to the analyzer, how this changes as a function of kinetic energy, and are there any implications for the data that we see in our survey measurement. So what we're doing is creating a set of images that have been noise enhanced. So we've performed outlier filter. We've also applied principal component analysis to noise reduce the data. And then we're going to select a pair of images over a wide kinetic energy range and overlay these images. And the first thing that we see is that we have a registration that is not quite perfect. So what would that mean for a spectrum that had a similar sort of imperfection? Well, what we'll do is perform a little bit of arithmetic on these images and create an image which we can partition the signal from different zones on the image into where there's gold from both of them, where there's gold from one but not the other, and vice versa, and where the void is. So we're going to do this by creating a false color image, and the false color image, we will then save the index from the false color image in both of these images. They'll both provide us with a binary image that's 0 or 1 depending on whether there's gold or no gold according to the intensities that we specified, so that when we overlay them we can now see we've got yellow where there is gold, green where there's gold from one but not the other, and then there's another color that will give us the void. And in order to create a useful image, what we'll do is perform a calculation that takes binary images, that's 0, 1, and we'll produce a binary image from these both that will either be 3, 2, 1 or 0, and therefore we can identify using false colors these different zones that are of interest to us. So creating a false color image, you can see black represents where the gold overlays between both of them, blue and green are where there's a shift, and red will be the void. And if we make this our false color mask, let's just verify that appeared, and yes, there's a false color mask. If we make this the false color mask and then we create spectra pixels, and we'll do this from the raw spectra pixels, so there's no processing interfering with the spectra that we're going to now calculate. So we'll remove all the outlier filtering, all the PCA noise reduction, and then we can sum from these raw spectra. We'll end up with 4 spectra that represent the 4 colors from that lookup table there. So we've got red, blue, green and black. And when we sum them, we see these lookup table indices 0 to 3, and the black represents where the gold is, the red where the void is. So even in the void there seems to be some gold signal being reported. And then we have spectra which are characterized by different backgrounds, as you can see for the lower kinetic energy. Now let's try and understand what this means. If the background is moving as a function of kinetic energy, what we'll do is we'll create a pair of regions, one for the gold 4F and one for the gold 4D. There is also the gold 4P 3 halves, but there's also some copper in this, and I believe there's an overlap of the Auger from the copper, so we won't look at the 4P 3 halves. We'll just use the 4D, which is the doublet pair you see here, and the 4F. We'll propagate these regions to the other spectra. We'll put up an annotation table. So we're really looking at the ratio of two gold peaks, so in principle they should be 1 to 1. Well, we can immediately see that this one is not 1 to 1. It's 62 to 38. And we'll propagate that so we can have a look at the other spectra. And here we have, well, that's the other way round. We've got more 4D, less 4D, and that's it, what you'd expect 1 to 1. So that fourth, the one with index 3, that's the where the gold signal overlaid from both of those images from different kinetic energies. Let's just illustrate this using another feature here. So change color for each tile. What this is going to do when we display them, the spectra, we can see that each tile color has changed. So we can now compare the color of the spectrum against what you see in the lookup table. So black will be where they overlay together. And we've come up with 4 different spectra. All of them seem to offer some amount of gold, albeit very small amount in the case of the red zone. But we've got gold where they overlap, and we get a good quantification from that. But from these other zones we do not. These two images that we use to construct this false color table allows us to see the difference in registration between different kinetic energies for images of the sample as passed through to the analyzer. If we now take the 4 spectra that were constructed looking at the differences in that registration, we can now break down the data set into a more systematic, smaller area analysis based on the chessboard pattern, and then we can use the 4 spectra that we calculated as the basis functions to see how these small area analyses reflect these registration issues. So what we'll do is, after we'll adjust some colors here, what we'll do is overlay the data in the active tile that represent the 4 spectra from the registration spectra. We'll select the 16 spectra that were calculated from the chessboard, and then we'll create linear least squares solutions where we can then look at how each one of these areas that were within the chessboard are constructed from the 4 spectra that came from the registration image. So let's just see how this all relates. We'll create 16 spectra overlaid so we can see how the linear least squares solutions are constructed, and we'll arrange these so that we can see them relative to the chessboard pattern. So there's the chessboard pattern, and we'll just do a bit of rearrangement here. And what we want to do is display these spectra and the reconstructed spectra in terms of a least squares fit in using the colors that were from that chessboard. And again, we'll use the color for changing the color per tile, so we can then relate the spectra that are being displayed, these colours here. So you can now see how each one of these spectra and the breakdown into those 4 spectra from the registration images are organised. And it's quite clear that from different zones you get different spectra and different compositions.